let's show the proof that if a certain Lebesgue measure of a certain set be equal to 0, then that said set is measurable. Please don't be confused with the idea of countable before, because just a short reminder, if a certain set is countable, again, if a certain set is countable, then its Lebesgue measure, outer measure rather, is 0. Now, it doesn't work the other way around. It doesn't say that if the Lebesgue outer measure is 0, then the set is countable. Here, if the Lebesgue outer measure is 0, then that set is measurable. Okay, so we are going to show that here, but of course we are going to use here the definition for measurable sets. We know that a set is measurable. Okay, let me write here the definition of measurable set just for our guidance. A set, okay, a certain set is measurable. Let's say E, a subset of R, is measurable, okay, if for each set A, set of subset of a set of real numbers, we have the Lebesgue outer measure of set A is equal to the Lebesgue outer measure of the intersection of A and E plus the Lebesgue outer measure of the intersection of set A and the complement of E. So hopefully we could show this relationship for us to say that our set E is measurable from the given that the Lebesgue outer measure of set E being equal to 0. So let's start with this proof here. Of course, we are going to assume that the Lebesgue outer measure of E is equal to 0. So we have here, let the Lebesgue outer measure of E be equal to 0. And since we would like to show this form, we will be introducing set A. And assume or let, you can use assume, suppose there exists set A element of set of real numbers. Hey, now we're going to look into the importance of these two portions. Hence, there should be existence of intersection of both A and E. Before we continue, let me have here, again, there should be intersection. So you have here set A, and this would be our set E. There should be intersection. So for the Lebesgue measure, we can have here, the first one is intersection, so this one here. Okay, this is the intersection, this other one. So we're going to take the Lebesgue measure of that, and of course A later on, and connect it with our Lebesgue measure of E. But this is actually, what is this? This is actually, again, the A intersection E is actually just a subset of set E, right? This is our set E, the red one, and this black portion here is just a subset of set E. At the same time, if we talk about the A intersection E complement meaning everything outside the red portion, so you will have this blue here, okay, so that's actually outside. And if we're going to connect this to our A, so we have A, so this is A intersection E complement. That would mean again, the AE complement is everything outside this one, so this will include everything, but the intersection of 2A is this blue color region here. So this is blue, this is the blue one. Let me change the color of this text so that we would be guided. So you have here A intersection E complement. This is actually a subset of A. The black one is the intersection of A and E. It's a subset of set E. The blue one is the intersection of A and E complement, which is a subset of A. Why do we do this? Because, take note, we were able to draw a relationship before that if A is a subset of B, then we also proven this in a separate video. The Lebesgue outer measure of A is less than or equal to the Lebesgue outer measure of B. So with this here, these two, hence, or thus, we can use thus, Okay, the Lebesgue outer measure of the intersection of A and E is less than the Lebesgue outer measure of E. And the Lebesgue outer measure of A intersection E complement is less than or equal to the Lebesgue outer measure of A. Okay, so with the use of this. Now, take note of this. We would like to show or reach this portion. Now, Lebesgue outer measure of A already appeared. The Lebesgue outer measure of A and the intersection with E complement also appeared here. The Lebesgue outer measure of this already appeared here, and this is actually 0. Okay? So with this, let me take the first equation on 1. Since the Lebesgue outer measure of E, this is E, sorry, let me use parentheses. Again, going back here, the Lebesgue outer measure of E is equal to 0 as identified on the assumption. And since if this is 0 and this is greater than or equal to that, what would this tell us? And then the Lebesgue outer measure of the intersection of A and E must also be 0 as well. Why? Because this is 0 and this is greater or equal to that. And since the Lebesgue outer measures are measure functions and they'll all be positive or greater than 0 rather, then this is also 0 itself. And what does this tell us? Take note that if we have to shift this to, you will have the Lebesgue outer measure of A, just to make sure that this will arrive to this form, is greater than or equal, again, take note, we reverse the operation, the Lebesgue outer measure of A intersection E complement, right? Now, if we're going to add 0 both sides, okay? So, if we're going to add 0 both sides, it doesn't change the inequality. But 0 can be represented with this. So, the Lebesgue, then, the Lebesgue outer measure of A is greater than or equal to the Lebesgue outer measure of A intersection E complement plus this, the Lebesgue outer measure of A intersection E, which is actually just the 0 earlier. Now, this has two different forms. Okay, this has two different forms. The first one is that the Lebesgue outer measure of A is greater than the Lebesgue outer measure of A intersections the E complement plus the Lebesgue outer measure of A intersection E. Okay, that's one. The other one here is that equality equal to the Lebesgue outer measure of the intersection of A and E complement plus the Lebesgue outer measure of the intersection of A and E. So this comprises this statement because that's greater than or equal to the said expression. Now, what about this one here? Just this statement alone, we can now say that hence E is measurable. Why? Because this satisfies the definition that a set E is measurable if we can guarantee this one here. And these are all possible starting with the assumption that the Lebesgue outer measure of E is equal to 0. And all of this tells us that again E is measurable. Don't worry about these two situations. We just want to see this for us to claim that E is really measurable. That's it for the proof of this statement. Thank you very much for watching.